And so our first speaker is Natalie Reznikov. Natalie is an assistant professor at McGill. Natalie says she's been using Dragonfly since 2017. I bet we have some graduate students that were still in college back then, some babies in the room. So Natalie says she learned about Dragonfly because we have a very loud evangelist in Montreal named Nicolas Pichet, and so she learned directly from the horse's mouth. And so I'm so glad that she got connected with Dragonfly and is going to tell us about some really terrific bone research here. So Natalie, I'm going to put up your presentation and I'm going to give you the mic. Let's welcome Natalie Reznikov.
Oh, hello. Hi. Thank you so much, Mike, for your kind introduction and for this opportunity to open this lovely workshop. And I will tell you a story about how, with the help of 3D imaging, we can unlock the history, the functional adaptations of bones. And I will start it with a personal anecdote from my studenthood from 2013, when I and my buddy at the Weizmann Institute, Jonathan Ben-Zvi, we were planning an experiment on analyzing trabecular bone properties in response to compressive loading. And because both of us, Jonathan and I, we were trained primarily as dentists, so the natural model for us would be to use a human jaw, because we knew from human anatomy that a jaw would be full of trabecular bone tissue. And nothing can be simpler than having teeth occluding, right, and projecting compressive forces onto the bone beneath. But we couldn't get a human sample for our experiment, but we knew that pigs and humans share a lot in common, and we got a pig jaw. We were very proud and expected to harvest a lot of trabecular bone for the experiment. And we cut it open and found out that it was hollow. That was a little bit of a shocker for us because, well, you know, your leg bones are hollow. They're hollow tubes. As in the pig bone, that hollow structure extended from the molars to the incisors. So there was no trabecular bone under the teeth at all. And classic beam theory teaches us that tubular structure, hollow tubular structures, are perfectly adapted for bending, but not for compression. So we had no stuff to work on, and we didn't know how to live with this notion that form follows function in bone. But Google gave the answer eventually, and indeed, in pigs, bone does follow function because what this pig is doing, she's digging roots out of the soil. So she's imparting a humongous bending momentum on her mandible. And the jaw of the pig is perfectly adapted for exactly this role. So it's a different way of loading bone in comparison with what we do. So, and still, what is trabecular bone for? If we look into this video featuring a sheep femur, we may appreciate that trabecular bone, this lacy, delicate structure, is primarily located near the joint. And throughout the body of any large animal, you will find trabecular bone where things move. Perhaps it is adapted for multi-directional loading, because when things move, you may expect a loading vector coming from any direction. Plus, bone would have different texture. Sometimes it's very uniform and delicate. Sometimes trabeculae merge and form these Gothic arches that look like buttresses. So can we get the idea of a function from the structure? And for more than 2 decades, there had been a method, a canonical method of inferring bone function from the structure by calculating the anisotropic coefficient. There are many ways, at least 3 popular ways of calculating anisotropy. You can get your mean intercept length, you can get star volume or orientation volume, stuff like that. And all these classic methods actually require some degree of cropping of your volume of interest to a more or less isotropic shape, not to introduce any bias into the calculation. Then it would give you a value that would be statistically robust if your computation volume is big enough, so like 5 millimeters at least, to have sufficient number of repeats of trabecular and intertrabecular spaces. However, in a real specimen, in a real bone, you move a few millimeters here or there, you will end up in a totally different texture of bone. Some trabecular are fine and gentle, and some are fusing into chunky formation, and some are co-oriented. So here we are facing the classic problem of digital image processing. We have to marry high resolution and functional context. Enter Dragonfly. So I have a generic shape here, a parallelepiped. Imagine that we split this isosurface into units of surface, say triangles, and project elementary vectors sticking out from each triangle, and then just count them. So in the parallelepiped, there will be 2 elementary vectors emanating upwards, and there will be, say, 20 vectors emanating forward. And if we compare these numbers, flip them over to get a reciprocal, we will say quantitatively that the parallelepiped is an anisotropic structure, and it is oriented vertically. So once we can do that predictably on a simple surface, we can also extend the algorithm to a more complex surface. And say we have this segmented volume of trabecular bone, we call it our working surface, and we split it into elementary triangles that would be very small, and then construct these elementary vectors. So as my cartoon shows, in one area, in one spot, that would be as small as 1 millimeter in diameter, we would have all the vectors sticking out in the same direction, so they will add up, and some would be a little bit misoriented, so there will be some cancellation. And for every position, we can apply a vector operation and normalize it into a fraction of a unity, and that would be a vector map. So a vector map of the same sheep femur that I showed a few slides ago, made of 5 million vectors. If we plot them from low, blue for low, to red for high, can show us some interesting things that we may not capture by a naked eye. For example, in here, you can see my cursor, but in this inset below, you see that there's the bump on the right is blue. That's the head of the femur. It is sitting in the socket. It's a ball and socket joint. It would be illogical to have any preferred orientation if this structure is kind of ready evolutionarily to receive loading from any direction. And the further we go towards the shaft of the bone, the more red, orange and red the structure becomes. But we can also borrow this notation from crystallography and color code X, Y, and Z axes as red, green, and blue. And then we will see even more interesting things. So for the head of the femur, we don't see, again, much of preferred orientation and an isotropic signature. But look at this, the major trochanter, where we have muscles, posture-maintaining, slow twitch muscles attaching to the bone, and minor trochanter, where we have another group of muscles also working very hard to keep the animal upright. So between these 2 points, we have a very smooth, uniform band of co-oriented trabeculae that start vertical and then go oblique and then connect the 2 muscle attachment sites. So what does it mean? Is it a tensile component of the entire bone? Who would think about that? We used to perceive bones as compressive elements by large. So now it's the time to make a short story long, right? We need to validate this study, right? And to properly show that anisotropy is a meaningful descriptor of bone, we need to compare, let's say, same skeletal element, same bone, but loaded in different scenarios. And I was very lucky to work for a few years in London in the UK and to get access to one of the most terrific pathology collections in Europe, the Gordon Pathology Museum. So here on the right, you see there's middle aisle contains all the skeletal pathology specimens, and I got 2 of them. And they were the following. One is called the clubfoot talipes varus, which is an inborn condition where by abnormal muscular tone, the foot is averted so that the heel is essentially pointing upwards. So the individual with this condition could never walk and died at age 16. Of note, Lord Byron also was afflicted by this clubfoot condition, but that's not his foot. And the second specimen is a block of several bones fused in one piece. It is called ankylosis. It is an acquired condition caused by chronic infection and inflammation. So this donor was walking normally until the age of 20 or so, until the infection set in. And then he had about 2 decades of very difficult lifestyle until he got his foot amputated. So these 2 conditions have kind of extreme scenarios where normal bouncy, shock-absorbing bipedal locomotion would be impossible. In one case, the foot never walked, was kind of disused, and in the other case, it would be, if you will, abused, because when the foot is rigid, then the movement is quite jerky, comparable to walking on the peg leg. So I had an undergraduate computer science student, Huiling, who did really terrific job fixing the scans of these museum specimens. The problem with the clubfoot scan was that it was mounted in the end of the 19th century, before the advent of X-rays in biomedical research. So it was full of fixtures and wires inside that were casting horrible artifacts inside the scan. So they had to clean it all up with the help of a neural net, and then to label all the bones individually. It was easier for her with the fused foot, because it was one piece, there were no wires, but the task was to find the boundaries between all the tarsals and metatarsals. So she did that also really well, and we ended up with several specimens of physiological use, abuse, and disuse, so to say. Where would I take normal feet? From teaching anatomy collection. That's easy to get. So I had 3 conditions: physiologic loading, once normal, then abnormal loading, and always ever abnormal disuse. And for the human calcaneus, the mapping algorithm would work pretty much in the same way. Let's say we land with the probe at some position. If there is a spherical pore, all the vectors emanating from the surface would cancel each other out. There will be 0 measurement for this position. And if we have a continuous surface, all the vectors would add up, and we will have a long resultant vector that will register in the 3D vector map. So we will raster until we get a color-coded rendering of several million vectors. So here, you can appreciate perhaps the arrows that are sticking out from the picture in different directions. So every arrow stands for this digital sphere of influence, where every elementary unit of surface has been transformed into a vector, and then kind of calculated and averaged and projected on orthogonal axis. And the same volume is shown by magnitude and by direction. And if we put everything into its pristine anatomical context, we will reveal a pattern of anisotropic trajectories. So there is a dorsal band of co-aligned trabeculae that goes from the talocalcaneal joint towards the Achilles tendon. And then there will be a plantar band that goes like parallel to the ground. There is the Achilles band of consistent anisotropic alignment of trabeculae, and there is also this perpendicular to the screen band of trabeculae that are oriented in the y direction, in green, right? And it turns out that all these bands can be explained by physiologic function and by the attachment of muscles and tendons to the foot. So the weight of the subject is applied from the top, and Achilles tendon is pulling upwards, right? And the plantar fascia is pulling forward, and peroneal tendon is applying tensile force to this green formation on the right picture. So we have, in fact, two bands that are standing for compressive loading and two bands that are standing for tensile loading, the Achilles and peroneal. Now, using the same method of rastering, we can also measure a scalar value of volume fraction, which is the opposite of porosity, and we can compare an anisotropy by its magnitude, by direction, and volume fraction altogether. And it turns out that these metrics are totally independent. We can have an area where anisotropy is low, but volume fraction is high, or we can have anisotropy high and volume fraction high, or anisotropy high and volume fraction being low, and both being low. So any combination is possible. So these metrics cannot replace each other. We should measure them and analyze them independently. So let's compare three non-pathologic heel bones. Once you see an example, you can say you have seen them all. They're all similar. They have the same pattern of anisotropic bands that are can be related to the bipedal locomotion style that we all share. And if we take another non-pathologic calcaneus and compare it with the two museum specimens, we will appreciate that something goes wrong in the cases of congenital or acquired disuse of bone. In the case of the club foot, you will see that it's almost hollow. It's very delicate and empty. There is not much material because there is no loading, and nature is parsimonious, and if there is no work to be done, there is no material to support the function. In the middle panel, E, this clubfoot calcaneus shows a very patchy, inconsistent, haphazard anisotropy pattern. There is no, you won't find a consistent trajectory. And that again fits the idea of severe disuse. And in the case of ankylosis, the total amount of bone tissue is actually higher than in the normal bone. It is also patchy and coarse, which is consistent with the state of chronic inflammation. And this bone, the ankylotic specimen in the bottom row, actually started okay with the physiologic locomotion, but lost it at halfway before acquisition of the specimen. And we may appreciate that the anisotropy trajectories are vanishing. We have this dorsal trajectory still visible, but the rest is quite inconclusive. So to summarize this story about bone adaptation that we can read through a 3D map of anisotropy vectors is that the inner structure of bones is in fact continuous with the orientation and role of muscles and tendons. So it would be inaccurate to view skeleton as a standalone structure. Must be viewed as integral part of the connective tissue system. To paraphrase the Anna Karenina principle, normal bones are all alike, and every abnormal bone is abnormal in its own way. We can reconstruct the loading pattern by looking at the microarchitecture, but we should be ready to tackling this enormous multi-dimensional landscape, because we have the conventional 3 dimensions X, Y, and Z that stand for size, shape, robustness, outer morphology. And now we have the time, because we accrue functional adaptations with function, with age. And then there is also anisotropy by its magnitude, anisotropy by direction, and volume fraction, that is a separate metric. And we can also add other things, or let's say network connectedness and so on. Perhaps we will start truly unraveling the mysteries of bone loading history when we have a control of all 6, 7, or 8 dimensions of functional adaptation. And with this, I would like to thank the people without whom this work would be impossible. Matthew Gendron of ORS and Nicolas, Bill Edwards of the Gordon Museum, who provided the food specimens, and Farah Ahmed of Natural History Museum in London, who allowed me to scan them at her Nikon Metrology MicroCT scanner. And thank you for your attention.
That was terrific. Thank you, Natalie. So I'm not sure how we're going to do this yet. So Robert, if I speak in this mic, does that go to the room or does that go to the Zoom audience? Zoom. All right. So Natalie, I'm going to let you stay at the podium. I'm going to chase you around the podium. Keep going. The reason I'm up here instead of just I'm going to make sure that whatever questions we get from the audience, I repeat so the Zoom audience can hear them. So thank you, Natalie. Do we have questions on Natalie's talk? I'll start up front right here.
Hi, yes, good morning. My name is Michael Hernandez. I'm a first-year PhD student here in Michigan. I want to ask, what do you believe to be like the evolutionary or like the biological reason for the localized anisotropy difference in the bone?
So what is the biological driving reason for the localized differential anisotropy in the bones, if I have your question right?
It's a terrific question, thank you. So we all start our life as generalists. We don't have any specialty. We don't exercise in a particular way by, being a swimmer, being a ballet dancer, being a soccer player, right? And in juvenile bone, it's good for everything. It's pretty much isotropic. But with strenuous and repetitive loading, certain directions are getting reinforced, and other directions that are idle are getting subdued. So eventually, not overnight, but over years and decades, certain directions that are subject of repetitive forces just get highlighted as anisotropy bands for, thanks to remodeling and orchestrated cellular activity of bone resorption and deposition.
And Natalie, if you want to step back in front of the podium, make sure we have the microphone taken care of. Okay, more questions from the audience? Yes, Benjamin.
Yes, so I have a question about the pathological specimens that you looked at.
Yes.
So do you expect that the anisotropy would be different in the non-pathological foot from those specimens? So for example, if one foot is a club foot and the other foot is a regular foot, would you expect that the anisotropy pattern in the non-club foot would give any hint that the other foot was a club foot and that there was some difference in the walking mechanism?
Right. So if you want to step in front of so you're just in front of the mic like you were for your talk. So the question is, when you have a pathological specimen, you've got a bilateral symmetry like 2 feet, and you have one pathological foot and maybe one healthy foot. Would analyzing the healthy foot, if that was all you saw, would that give you a clue? Could you infer something about the pathological specimen from the observing just the would-be non-pathological? Is that about right?
Well, they don't make them anymore, right? These are the specimens from more than 100 years ago. And they were procured before the time of public health care and preventive medicine and antibiotics. So you won't find them anywhere. So it's n equals 1 for each pathology, right? But it would be great to try to dissect it to the level of individual variation and individual locomotion patterns.
Other questions from the audience in the room? I'm going to go to Carl.
Yeah, just a little follow-up on the previous question. If you were to compare, let's say, 2 groups of individuals in terms of the 3D anisotropy and looking at distributions of them, have you moved into that type of analysis of comparing those distributions statistically?
Yeah, so I think it's sort of a meta question going up from the individual bone anisotropy map to populations. Do you have a framework, or have you started to ask the question of comparing statistically the population, the anisotropy of a population of one group to the anisotropy of another population?
Yeah, that's our work in progress, because every map would be would contain several million vectors, so we have to streamline it somehow, maybe by multivariate analysis, to extract the most salient features that would be generalizable over a large population or a small population or occupational pattern, something like that. And we don't know how to do that yet.
Do we have a poster or a talk on atlas approaches?
Indeed.
Okay, so I would refer Carl to a poster on advancing a pattern or a framework for doing statistical observations by projecting measurements onto an atlas and then comparing the statistics of the atlas, if that makes sense. So for those of you that are remote, if you had registered and come in person, you get to see the poster. And then the next question right here. Oh, well, there's only 10, so you won't get lost. Whose poster is it? Is it yours, Benjamin? So Benjamin here in the second row is giving a poster on atlases. Yes, let's do one more question from the audience. So I'm gonna go over here to Joshua.
Hi, I was just wondering, in Dragonfly, can you control the size of the triangle of the tetrahedral mesh, because you're outputting millions of vectors? I was just wondering, can you control that kind of size distribution of how big the triangles are created? Because all the vectors are perpendicular to the normal, right?
Yeah.
And have you found that you need to make millions, or can you get away with less and still get a full map?
So the question is about sorry, Natalie. The question is about the mesh observations, and a surface mesh itself is just a tessellation of a bunch of triangles, and it could be millions of triangles or hundreds of thousands of triangles. Do you use anything in Dragonfly to tune that sampling or that population so that maybe instead of observing several hundred million, maybe you're observing a few 100,000? Is that a
Yeah.
How's that question?
So there are two aspects to it, and I planted the slide expecting this question. So, so first of all, you can simplify your mesh, and this is similar to what you do in finite element analysis, right? So you kind of you're looking for the plateau when the precision of computation stops outweighing the computational cost. So you can simplify the surface, produce less triangles, and then you will have a more like smooth, averaged anisotropy map. Now, for every position where you measure your anisotropy vector, you can expand the sphere of influence or shrink it. And if you are working with a very tiny probe, then everything would look totally anisotropic, just like from a point of view of a single human, Earth looks flat. But if you're expanding the volume of analysis, then individual local variations start kicking in until you average things over the whole object of interest, and everything becomes like isotropic totally. So it's a matter of adjustment and nudging the parameters, but as a general rule, well, you can optimize the number of triangles, and the sphere of influence should equal a period of repetitive features times 2 by the Nyquist rule.
Thank you.
All right, let's thank our speaker again, Natalie. That was terrific. Thank you so much.